Welcome to Quant Cop, Math Crimes Division, Episode 2. Today we're going to tackle linear regression. I can't stand when people use this stuff on financial markets. It's just the wrong tool in the wrong place. It's a violation of Wittgenstein's ruler to the nth degree. So let's take a look at here. So I took two stocks, not related in any which way possible. Ford, maker of automobiles, and International Paper, a wood paper products company, use wood. So I went back to 2000, and regressed the daily returns. There you go. You got your buckshot scatter plot. You shoot a line through it. Correlations P is 50%. So the R squared is 0.25. Now, if you believe anything comes out of a Wall Street sell-side desk, they're going to tell you this Ford has some relationship to International Paper, but we're going to prove that that's not true, and we'll prevent you from making these simple mistakes again. So, okay, let's now this is a static picture, right? We're looking at years and years of returns. Let's put it into motion. Let's take a more dynamic approach. So here we go. We got rolling R squared, a 3-month rolling R squared of the daily returns of Ford and International Paper. As you can see, this thing oscillates from 0 to about 90%, right? Up, down, up, down, up, down. Are you starting to get the point? These two processes are not related. I don't care what the statistics tell you. And I'm going to explain to you now why this is a mistake. I'll give you the simple explanation first, and then I'll give you the more scientific explanation second. So here we go. Okay. Why is linear regression, or even nonlinear regression, the wrong tool when you're dealing with financial markets or any social science process? The simple statistical reason is that you cannot compare two time series or processes that do not have the following things in common. One, or A, they're co-integrated, and B, they have stationary distributions. In this case, they had both, neither. Both of them had neither. They weren't co-integrated, and neither one of them had a stationary distribution. Most securities don't have stationary distributions, and don't tell me you're going to alter it and make it a stationary distribution. It doesn't work that way. So an illustration is, so if those two properties do not exist, then you cannot assume the following reductive connection, right? That delta x, the independent variable, affects delta y directly, the independent variable. This is essentially astrology under a different name. So now I'm going to get deeper into the science of this and why you can't use these tools. So, what's the more scientific reason behind you not being able to use these tools? So, financial markets are complex adaptive systems whose rules are not constant, but change based on the actions of the players in what phase of the system is currently experiencing. Markets are nothing more than discounting mechanisms. They discount fundamentals, technicals, whatever you want. But today's price is a discounted present value of all expectations. That's what the price is. So they're essentially a gestalt, right? A financial market. Why? Because the whole is greater than the sum of its parts. They're an emergent process. What is an emergent process? Well, think of an apple seed. I take an apple seed, I plant it. I can get 100 apples from that one seed. That's an emergent process. The total is greater than the sum of its parts. This came from an apple seed is 1, it becomes 100. And all the seeds you get from those apples can plant hundreds of apple trees, right? Here's another one. Two humans, they have sex. 9 months later, they end up with 3 people. These are deterministic, chaotic processes that are sensitive to initial conditions, delays, feedback, and networking effects. You cannot use reductive linear stochastic models on these type of emergent processes. It's not effective. So if you wanted to look at a model of this process, we'd say Delta X is a function of delta X, delta Y, delta Z, dot, dot, dot. Whatever is coming in and incorporating itself into this process and feeding on itself is how you have to model these things. Markets are not a statistical problem. They're a stock and flow modeling problem in the sense that you want to know what agents are doing and how much of their expectations have been built in. Each phase in a market has a separate set of rules governed by feedback flows and networking effects. These tend to be a cycle, right, between self-reinforcing and self-correcting, where in markets we call them risk on, risk off. It tends to be this feedback mechanism that's working in a positive correlation with price until the last person gets on board the boat. And then it only takes a small wave to topple that boat. So they reinforce in one direction, and then the rules change, and they start being reinforcement in the opposite direction, right? This is a perpetual cycle between, we call it emergent order, or trends, or risk on, and some sort of phase transition, or reversal, and then entropy, or risk off. This cycle is perpetual. It's cross-sectional, it's cross-temporal, and it's persistent. Now, the only thing that changes in this cycle is the depth and duration of this cycle, depending on how crowded or how consensus the market becomes. That is not a statistical problem you need to solve with linear stochastic modeling. So, what have we learned today? First, don't be a linear stochastic fool. You need to embrace complex system science when modeling real-world social science processes. Think of markets more like weather than blackjack or poker. Because in blackjack or poker, you have a finite distribution with a fixed set of rules. Even in no-limit hold'em poker, bluffing doesn't change the odds. It just clouds what you're representing as the odds based on what you're pretending to have in your hand. Not so in a complex system. In weather, it's temperature, precipitation, jet stream, barometric pressure. Those initial conditions all come together and create a storm. Or in the opposite, they create clear and sunny skies. This is much more complex. This is a deterministic, chaotic process. So that's it for today. Next time we're back with another breakdown of the problems that quants face with the tools they've been taught. Till next time, aloha.